I want to start today with a challenge that will push your logic to the absolute limit. Before I reveal the data NASA documented just hours ago, I need you to go to the comments right now, type the name of your city, and answer this. Do you believe we are the first civilization on this planet to try and decode an interstellar message, or are we simply the third iteration currently undergoing a cosmic audit? Don't answer lightly. As we speak, the Object 3 I-Atlas is emitting a frequency that has, if you stay until the end, you'll understand why top-tier scientists are using the word evolving instead of fading. But if you think this is just another rock, you might not be ready for what the James Webb Telescope just captured deep within its core. Are you an observer or are you part of the experiment? Tell me your theory below, because the patterns in your comments might reveal the truth NASA is trying to ignore. NASA has just released a fresh batch of documentation on Comet 3 Atlas, and there is one specific word that keeps surfacing behind the scenes: evolving. It isn't done, it isn't settled, and it certainly isn't fading away into the dark as many expected it would by now. If you have been following this interstellar visitor, you know that its journey through our solar system has been a series of surprises. And today's update suggests that the most interesting chapters might still be ahead of us. These latest numbers don't just describe where the comet is today, they offer a profound hint at what it is actually. Routine part of the job, standard brightness measurements known as photometry, using the same filters, telescopes, and geometric corrections as previous sessions. The goal was to confirm the comet's expected decline. On paper, the physics are straightforward. As a comet moves further from the sun, the solar heating drops, the internal activity should settle, and the brightness should follow a smooth, predictable downward curve. In a normal scenario, every new data point should land a little lower than the one before it. However, the newest measurements for 3I Atlas simply refuse to follow that rule. When researchers plotted today's magnitudes over the predicted fading curve, the real comet sat consistently above the line. It isn't undergoing a massive explosive flare, but it is undeniably brighter than it should be at this distance. This wasn't just a single outlier or a glitch in the data. Multiple measurements have clustered along a new, slightly higher trend line. And this is our first clear evidence, but the brightness is only the surface of the story. The real drama is hidden in how that light behaves over time. When the team took today's brightness data and folded it over the last known rotation period, the pattern didn't line up with previous models. The main peak, the moment when the most active regions face both us and the sun, showed up slightly earlier than it was supposed to. Even more intriguing is that a secondary bump in the light curve, which used to be small and highly inconsistent, has now transformed into a steady and repeat feature of every single rotation. To get the entire light curve to align, scientists had to shorten the rotation period once. And again, this comet is spinning faster and faster. More importantly, the very shape of the light curve has evolved. And what was once a single dominant source of activity has become a much more complex arrangement. We are now seeing multiple regions flashing in a predictable order as the comet turns. This is a definitive sign of evolution. It isn't just about having more but a fundamental change in the pattern of that activity, and then the focus shifted to the visual data. Today's deep exposures were stacked and sharpened with extreme care, aligning perfectly on the nucleus so that every possible detail of the Comet tail could be pulled out of the background noise. So if you were to compare last week's image stacks against today's, you can literally see the object evolving before your eyes. In the older images, the inner coma looked like a simple, stretched globe. It was asymmetrical but relatively basic. In today's stack, that bar has developed a complex internal structure. There's now a distinct bright knot on one side of the nucleus and a softer lobe on the other. Wrapped around them is a faint arc, a partial ring that looks like a wave caught in the middle of expanding outward. And just beyond that, if you push the contrast high enough, a second, wider arc becomes visible. Marking the rim, of what the comet was doing the moment that material left the surface, that new inner arc simply didn't exist in earlier images. It is fresh further down the tail. A subtle fork has appeared. While the main spine still stretches away from the sun, a faint second streamer is now peeling off at a slightly different angle. This is exactly what you would expect to see if a new jet oriented in a different direction adjoined the existing flow. The architecture of the coma is fundamentally changing. Beyond the visuals, there's the data that doesn't care about aesthetics, the orbit. Every new position measurement, whether it comes from ground-based observatories or heliophysics spacecraft, is fed into the orbit solver, while gravity dictates most of the motion. This comet is not a passive rock. Its active jets function like tiny thrusters, giving the nucleus an extra push that scientists track as a non-gravitational term. If the comet were truly calming down, this term would shrink and the orbital solution would stabilize, but today's results, so using yesterday's parameters, the predicted positions missed the actual detections by a specific margin. All the residuals leaned off to one side, which is a classic signature that the net push from the jets has rotated. When the solver was allowed to refit the data, it demanded two things: a slightly stronger acceleration than yesterday, S modo allowed, and a slightly different orientation for that push. So this new direction aligns perfectly with the new fork. Scene of the object keeping perfect pace with the visual changes in the coma. When you line up these three main diagnostics, the shifted brightness curve, the new structures in the coma, and the reoriented orbital thrust, you get a vivid picture of what evolving looks like in deep space. The question we have to ask is what this actually means for the interior of the nucleus. The most likely explanation is that we are watching the comet peel itself away in layers. When 3 Atlas first encountered the outer shell responded first. This loose dust and shallow ice created the wild flares and messy coma shapes we saw initially, but heat doesn't stop at the surface, it creeps inward. Deeper down, the comet's interior is likely a chaotic mix of ancient ices, voids, and fractures that were built up over billions of years in the cold of interstellar space. Each depth within that nucleus has its own unique chemistry, its own structural weaknesses, and its own threshold temperature. As new layers are crossing the tipping points, one layer activates and you get a specific mix of gas and jets that creates a certain rotation pattern, and then as the heat moves deeper, another layer wakes up. The composition of the debris changes, the dust grains might become larger or darker, and the jets themselves shift to new locations. Some old vents might collapse as new cracks open up. From the outside, we see exactly what today's data shows, because the active regions that survived the first violent encounter are now locking in. Even as deeper material joins the flow, the coma is becoming more layered because each burst from a new depth leaves its own mark, expanding outward and freezing into the overall glow. The orbital push is becoming more coherent because the jets are organizing themselves around a few dominant sources. So this is the optimistic view of evolution. A system under stress, finding an evolution under this kind of extreme stress is not free. Every new layer that vents adds fresh torque to the nucleus. Every increase in spin, no matter how small, increases the centrifugal force pulling on regions that are already damaged. Every time the thrust reorients, it means the internal fracture zones are being loaded in ways they haven't been before. We have seen this happen with comets native to our own solar system. Some of them manage to pass through this evolving phase and come out the other side as stable, albeit misshapen. Others keep evolving until their internal structure simply can't keep up. In one update, you might see a stretched core with complex jets, and in the very next, you're looking at a string of fragments. Currently, 3I Atlas is caught somewhere in the middle. It isn't in the explosive chaos of its peak activity, but it also isn't in the quiet fade of a spent comet. It is in that critical transition phase where the outer layers have been stripped. Today's data doesn't give us a final answer, but it states very clearly that this visitor is not simply dimming and drifting away. It is changing its spin, its venting, and its motion all at once. If we see these new patterns stabilize over the next few days, if the light curve locks in and the coma structure repeats, we might be witnessing the comet finish its evolution into a new, stable outbound state. If, instead, the peaks keep shifting and the shells keep multiplying, that ends in total disruption. We are watching an interstellar visitor change in real time, day by day. Most comets we study have been looping around our sun for millions of years. They have settled into predictable rhythms. Their surfaces are weathered, and they act like seasoned performers have memorized their lines. So 3I Atlas is different. It came from the deep freeze beyond our solar neighborhood, carrying materials that formed under conditions we have never directly sampled. It spent until it fell toward our sun for the first time in its existence. The heat it is feeling now is something it has never experienced before. What we are seeing isn't just activity, it is a violent, unscripted reaction to an environment this object was never designed to handle. It has no memory of this place and no stable pattern to fall back on. It is figuring itself out as it goes. And this is why the data keeps shifting. This is why it's doing everything at once, venting, spinning, cracking, and adjusting until something finally gives or settles. The brightness changes tell us the surface is alive. The rotation changes tell us the interior mass is redistributing. The coma structure shows us where the material is coming from, and the orbit shows us how. All those forces are literally steering the comet through space. It is a picture of an object under enormous stress trying to reach an equilibrium that might not, and rotational stress might simply be too much for its structure to absorb. If that's the case, what we are calling evolution is actually the slow motion beginning of a breakup. We have seen comets split before. Sometimes it happens in an instant. One day it's intact, and the next it's two pieces drifting apart. Other times it is a gradual process where the light curve starts showing double peaks and the coma develops two distinct centers before a fragment slowly separates. So in Atlas, there's no second nucleus in the images, and the light curve still behaves like a single object with multiple regions. Rather than two independent bodies, the orbital push is still coherent, but we are in the window where that could change at any moment. If the internal structure is strong enough, and if the vents don't break through critical load-bearing zones, this comet will survive. It will head back into the interstellar void. The light curve will become erratic. The coma will develop asymmetries that a single nucleus can't explain. And the orbit will struggle to find a consistent direction where it's too far away for anything interesting to happen. And we are watching it in the messy, dangerous middle. Today's data, the brightness sitting above the curve, the speeding rotation, the new coma structures all tell us that it is still throwing curveballs. It is staying more active for longer than the models predicted. The interior is still hot, the deeper layers are still bleeding energy, and the comet is still exhausting its mass faster than expected. Somewhere in that interior, there is a tipping point at depth where the ice runs out or the structure fails. When the comet finally exhausts its ability to evolve, the data will show it. The brightness will lock on to a steady decline, and the rotation will finally stabilize. But until that happens, we are in the unknown. And that is exactly where the most important science takes place. We will continue to watch every data drop, looking for the moment that tells us whether this visitor held together or came apart. Thanks for watching. Subscribe for upcoming space updates.